started with something out of the sheet already, right? What I want to do is, let me just give you a warm-up on problem solving on geometrical optics, even before we get very formally started with serious problem solving. Maybe I'll use some problems from this very sheet to get you an idea of the virtual object, the virtual image, the real object, the real image. Let's all cement it together, and with the help of some problem solving. All right. So let me illustrate some problems from the sheet, and then we'll get started formally from the sheet. All right. So what I'll expect out of you is, we'll take up a problem, for example, from the sheet. You read the problem at least. I'll explain the problem and solve it for you. Will not give you time for these problems because I want to use these as illustrations. All right. Go ahead and read problem 18, for example. All right. Let's set it up then. We have a small strip of a plane mirror A. It's a plane mirror A set with its plane normal to the principal axis of a convex mirror B. And placed 15 centimeters in front of B, which it partially covers. An object is placed 30 centimeters from A. Object O placed 30 centimeters from A. And two virtual images formed by reflection in A and B coincide without a parallax. Find the radius of curvature of B. Find the radius of curvature of B. Effectively the focal length, and then multiply by 2 to arrive at the radius of curvature. Now, look at the plane mirror in isolation. Look at the plane mirror in isolation. The object distance is 30 centimeters. The image is a virtual image formed 30 centimeters behind, right? That means 30 centimeters behind M is I. 15 centimeters behind the convex mirror is the virtual image of the object O formed by the plane mirror, right? This I also is the image of the object O formed subsequent to reflection from the mirror. Subsequent to reflection from the mirror, right? Convex mirror, from the convex mirror. That means, for the sake of the convex mirror, the object distance is like U equal to 45 centimeters. Image distance is V equal to minus 15 centimeters. All distances measured from the pole of the mirror in the direction of the incident ray is deemed negative. Opposite to the direction of the incident ray deemed positive. Alright. So, for reflection at the convex mirror, we have object distance is 45 centimeters plus 45. Why? Because to locate the object, I ought to be moving opposite to the direction of the incident ray. The image distance V is minus 15 centimeters. Yes or no? Why? I'm moving in the direction of the incident ray, and then that will give me the focal length 1 by V plus 1 by U equal to 1 by F for the mirror. So for the mirror, 1 by F is like a 1 by V, which is minus 1 by 15 plus 1 by U, which is 45. Yes or no? So that will give you the focal length. Multiply by 2 to get the radius of curvature. So this is like minus 3 plus 1 minus 2 by 45. So focal length is minus 45 by 2 centimeters, radius of curvature. Algebraic radius of curvature is minus 45 centimeters. That means the magnitude of the radius of curvature is 45 centimeters. How about that? Are you all comfortable with this? Conceptually, is there anything that's bothering you? The calculations are simple, but conceptually, any issue that bothers you here? And how does the convex mirror form the image? It forms the image because of reflection on the lower part. This O can see the lower part, right? That's how. So, and realize that for forming the image, you need two rays from anywhere on the mirror. That's all. It does not matter from which 2 points are you taking the reflected rays. You could assume the only difference that it makes is when you cover part of the mirror and obtain the image because of the remaining portion of the mirror, the image is going to be formed at the same position, but its intensity would be weaker. It's not going to be as bright but in this case, of course, it's a virtual image. So anyways, it does not make a difference. Do you realize that? It does not make a difference because rays of light are actually not converging to I in this case. Are they? Rays of light are actually not converging to I. So the concept is simple. Concept is simple, right? How's? Because of this. Plane mirror. See, this is how it happens. A ray of light that starts from O, incident on the mirror, gets reflected and seems to be coming from I. Commensurate with the fact that object distance must be equal to the image distance. That's how I is formed. And this also happens to be the image formed by the lower half of the convex mirror because the images do not have any parallax between them. So they formed at the same location. Are you there with me on this? Fair enough? 19. So let's look at 19. Yes, there are two virtual images. Absolutely. There is a virtual image because of this, which is at I, and because there is no parallax, you can conclude that the image formed by this is also at I of the object O. They coincide. Parallax means, there is, cause of parallax. There is no parallax here. No, parallax happens because of distinct images formed. That's parallax. No, even otherwise, see, in this case, it would have been distinctness of image, right? But otherwise, Parallax could happen because of a non-normal viewing. Non-normal viewing. All the images that you see are like normal viewing, but non-normal viewing can also cause parallax, right? Lack of focus can cause parallax. I mean, I'm not sure if you've done that experiment in school, the optical bench experiment. If you've done that, then when you move the lens, then you're trying to eliminate parallax. That means you're trying to focus the image. So many things can cause parallax, right? '19, please read problem 19. Have you read problem 19 already? Okay. A concave mirror, focal length 15 centimeters. Concave mirror. Magnitude of focal length being 15 centimeters. And a convex mirror, focal length 10 centimeters. Convex mirror and a convex mirror, focal length 10 centimeters. Placed coaxially, common principal axis, that is common principal axis, 70 centimeters apart facing each other. 70 centimeters apart facing each other. A 2 centimeter tall object is placed perpendicular to the common axis, 20 centimeters from the concave mirror. So, 20 centimeters from the concave mirror. You have a 2 centimeter object. You have a 2 centimeter object, OA, placed in front of the concave mirror. Find the position, size and nature of the final image formed by two reflections. The first one occurring at the concave mirror and then at the convex mirror. Alright. So, for the concave mirror, this is the object. Rays of light starting from this object get reflected, constitute an image. That image acts as a virtual object for this mirror, right? And then reflection occurs at this mirror, on this mirror, and a second image is formed. That's what is happening, right? So now for the concave mirror, first reflection. First reflection, that is concave mirror. That's given in the problem. Although, there would be a new series of images where the first reflection occurs here and then the second reflection and then the third reflection. There are two series of images obtained here. One series of image obtained by the first reflection occurring on the concave and then on the convex and then on the concave and then on the convex and so on and so forth. And the second series of images is obtained by the first reflection occurring here, the image of this acting as object for this, then again the image of this acting as object for this, and so on and so forth, right? So two series of images. In the problem, the author says very clearly, we are looking at the reflection first occurring at the concave mirror, alright? So now at the concave mirror, you have object distance equal to what? Plus 20 or minus 20? Plus 20, because we're looking at rays of light like this, moving opposite to the direction of the incident ray. So that's u equal to plus 20. What about focal length? Is it plus 15 or minus 15? Plus 15, because the focus center of this is located here. The focus of the concave mirror would have to be located opposite to the direction of the incident ray. So the focal length is plus 15 centimeters, right? So now that gives us an opportunity to find the image distance, right? So image distance 1 by v is 1 by 15 minus 1 by 20, right? 1 by v plus 1 by u equal to 1 by f. So this is what transpires, right? So that gives me like a 1 by 60. So v equal to 60 centimeters. Object distance is 20 centimeters. Image distance is 60 centimeters. What's the magnification? 3. I've told you, the magnification will always be regarded positive. We will not dare assign any sign to magnification as the books do. We will try and not interpret the sign associated with magnification. We'll regard that as extremely sinful. Okay? So, magnification is 3. That means if the size of the object is 2 centimeters, size of the image must be 6 centimeters. How about that, right? Now, question is, instead of using the sign of magnification to figure out whether the image is inverted or erect, we'll do some common sense analysis as to whether the image is going to be erect or it's going to be inverted, right? Image of O would be formed on the principal axis itself. Now, as far as A is concerned, you just take a sample ray. You take, suppose this is the pole of the mirror. You take a ray like this, right? Then at P, since this line passes through the center of curvature, this is a normal to the concave mirror at P. So then reflection occurs this way. So this is one reflected ray from A. So the image of A must lie on all reflected rays. So the image of A must lie on this reflected ray. And at what distance? 60 centimeters. So the image of A lies somewhere here, such that O is at O prime, A is now at A prime, such that this is 60 centimeters. This is 60 centimeters, and since the image of A is formed here, so if OA was like this, now OA is like this. So the image is inverted. The image is inverted. So don't take recourse to the sign of magnification to check on whether the image is inverted or erect. Just an ordinary ray diagram will tell you that the image is indeed inverted. The size of the image is 6 centimeters because the magnification is 3 V by U. How about that? Got me? Now, so this is 60 centimeters and therefore this is 10 centimeters. This is 10 centimeters. How about that? Right? Now, forget whatever has happened. O prime A prime is the new object. O prime A prime is the new object for reflection to occur on the convex mirror. For reflection to occur on the convex mirror, the new object is O prime A prime of size 6 centimeters located 10 centimeters in front of the convex mirror. Right? So now, forget whatever happened in the past. So, second reflection. The object distance is, so now it's like rays of light incident like this. This becomes our new reference direction. So this would be the direction of the incident ray for the sake of the convex mirror. So anything measured in this direction would be negative. Anything measured in this direction now would be positive, right? So then for the convex mirror, the object distance then is plus 10 centimeters, right? The focal length f minus 10 because the center of this lies here, right? So the focus will lie somewhere here, measured in the same direction as the incident ray, right? So negative. Focal length is minus 10 centimeters. So then 1 by v would be 1 by f minus 1 by u, which is minus 1 by 5, right? So v then is minus 5 centimeters. That means the image of this is formed 5 centimeters in front of the mirror. 5 centimeters in front of the mirror, yes or no? Now again, for the sake of this mirror, this is the object. This is the object. Now I want to see if this object is formed like this or it's formed like this. O prime would be somewhere here, not a problem, right? I want to check if A prime is formed below the principal axis or A prime is formed above the principal axis. Now it's an easy check to perform because think of A prime as an independent object. Forget all these rays. Think of A prime as an independent object. Think of a ray of light. I'm just dispensing this off so that you don't get muddled with the earlier rays. Think of this as an independent object, and A prime, think of this as an incident ray coming from A prime, right? And after being reflected, it goes like this, right? It doesn't lie here because it's negative. So the image ought to be lying there. So these rays of light seem to be coming from somewhere here. Seem to be coming from here. So the image of A prime must be formed at A double prime. The image of O prime to be formed at O double prime. At what distance? 5 centimeters to the right of the convex mirror, right? So the image now is erect. Same orientation, no change in orientation, right? The magnification is half. 5 by 10, magnification is half, yes or no? Size of the object is 6, so the size of the image is going to be 3 centimeters. Size of the image is going to be 3 centimeters, right? The nature of the image, real or virtual? Virtual, of course virtual. The nature of the image is virtual. If it's formed on this side of the convex mirror, it ought to be virtual. And now, this was the original object. This is the final image. With respect to the original object, is the image inverted? Yes. Is it magnified? Yes. What's the magnification? 3 by 2. 3 by 2 is the magnification, right? And formed 5 centimeters behind the convex mirror and is virtual in character. Are you all certain about everything that I have said here? This, right from there, yeah, that will constitute a new series of images. True. But the problem says that I want to look at the series of images where the first reflection occurs here and then the second reflection occurs here. Yes, this also constitutes a new image. With this as the object distance, this as the focal length, I can create an image of OA by taking the first reflection on the convex mirror. But the problem clearly says that don't take that series of reflection, take the series of reflection in which the first entity to get involved is the concave mirror, right? And of course, once again, this O prime, O double prime, A double prime acts as a virtual object for a third reflection by this, and an image will again get formed. That image acts as an object for this, and yet another image will get formed, and so on and so forth. Goes on. So there are two series of images, one in a manner that we've dealt with, the other one could have been by taking the first reflection on this, the second on that, and then on this, and then on that, and so on. No, not at all. Not at all. It's not a real image because do you realize that no ray of light could have gone past this barrier. So erect does not mean that it has to be real. Where on earth did anyone tell you that an erect image has to be real, or vice versa? That's not true. So don't judge real and virtual based on whether it's erect or inverted. I mean, the fact that there is no ray of light coming and settling at this point, it's only like these reflected rays seem to be coming from A double prime. That means that this image has to be virtual. You can't take a picture of this image. You can't take a picture of this image because there is no light present. There is no light present at A double prime. Right? It can't be photographed. Got me? Let me look at problem 20. I mean, when I say it can't be photographed, what I meant was, I mean, it could be photographed by capturing the reflected rays. What I meant was that if you are on this side of the convex mirror, even though this is the image and you are sitting here, can you click the pic of this? You can't, right? It's not like virtual images can't be photographed at all. But all that I'm saying is, you can't be sitting here and taking a pic of this because there is no light present here at all. It's like rays of light seem to be coming from this point, but if you are sitting here with a camera, then God bless you. Right? Let's look at problem 20. You mind reading that problem? All right. Let's look at problem 20. Alright, so we have a bright object P and a quarter cylinder of radius R. This is a quarter cylinder of radius R, and this is the plane surface of the cylinder. This is the plane surface of the cylinder. Refractive index 1.5 is placed on a table. A point object is kept at a distance mr from it. Find M for which P will emerge parallel to the table as shown. Now, let me tell you something which is incorrect first. Okay? I'll give you a wrong solution to this problem first. Okay? You tell me the mistake and then I'll give you the right solution. Okay? I treat this as a lens whose radius of curvature here is infinity, R1, right? This is a plane surface, so its radius of curvature is infinity. This R is R, right? And I can find the focal length of this mirror. I can find the focal length of this mirror. 1 by F is mu minus 1 into 1 by R1 minus 1 by R2. 1 by R1 is 1 by infinity, which is 0, minus 1 by R2. Right? And then I apply the formula 1 by V minus 1 by U equal to 1 by F, where I take U equal to MR and V equal to infinity. You know what I'm saying? I apply the lens equation 1 by V minus 1 by U equal to 1 by F, where U is MR, and since these rays run parallel to the principal axis, V is infinity, right? I use this. How and why is this incorrect? Where is it that we've gone wrong? Why not? Huh? Why can't it be treated as a lens with one surface as infinity, the other surface having radius R? Why can't it be treated like a lens? Of which one surface can be plane? Have you not heard of a plano-concave lens or a plano-convex lens? Huh? For? Absolutely, that's the answer. This certainly is a lens, but it's a goddamn thick lens. R is not small. R is not small. It's a thick lens. So 1 by V minus 1 by U equal to 1 by F is applicable for a thin lens. This certainly is a lens, but is a fat lens. Right? Very well said. Good answer. So that's where the mistake lies. You earn a chocolate from us. We'll give it to you when you accumulate 5. No, we'll give it to you before that. In any case, so I can't do that crap. 1 by V minus 1 by U equal to 1 by F is not applicable here. The lens is a thick lens. How do you check if the lens is thick or thin? Again, that becomes a question to answer. See, with the lens you would associate dimensions. What dimensions, what numbers do you want to associate with the lens? The radii of the two bounding faces, right? These are two numbers that you want to associate with the lens. Now, the maximum thickness of the lens should be smaller than these two numbers. That's when it's supposed to be a thin lens. the maximum thickness of the lens should be small compared to R1 and R2 both. That's when you can regard the lens to be a thin lens. In this case, this thickness is as good as the radius of this lens. So, not a thin lens. It's not a thin lens. Right? Now, so let's look at this situation from first principles, right? From first principles. We look at refraction on this. The image formed by this serves as the object for this. And then the image formed by this is at infinity. The image formed by this is at infinity. That's already presented in the problem. Alright. So then now realize that when refraction occurs on this plane surface, plane refracting surface, it's going from a rarer to a denser medium. So damn thing bends towards the normal, right? And it seems like coming from, not from O. For this surface will tell you that it's not coming from P, it's coming from some P prime. It's coming from some P prime. Right? And now, as far as this surface is concerned, realize that this distance and this distance are like the real depth, apparent depth distances. Yes or no? You know what I'm saying? This distance and this distance are like the real depth, apparent depth distances, and they are separated by a factor mu, where mu is 3 by 2 here. Mu is 1.5, right? And from the ray diagram, you can see that this is larger than this. So this must be mu times mr. This must be mu times mr. Yes or no? Right? So this is like mu times mr. How's that? Now, for refraction on the second surface, P prime acts as a object. P prime acts as a object, right? So, object distance for refraction on the second surface would be mu mr plus r. Mu mr plus r would be the object distance for refraction on the second surface, right? So, then for the second surface, the incident ray lies here, the refracted ray lies here. The incident ray lies here, the refracted ray lies there. So this must be the object space, that must be the image space. Even though the object lies in here, the object space is not here. The object space is glass. Why? Because the incident ray lies on inside glass. So this is the object space and that's the image space. So image space refractive index by image distance minus object space refractive index by object distance equals difference in the two refractive indices divided by the algebraic radius of curvature. That's the result that we're going to deploy here. So then, second refraction, image space refractive index, which is 1. This is the image space refractive index by image distance. Image distance is infinity, right? It's inappropriate to write like this, but for the sake of understanding, right? Image space refractive index by image distance minus object space refractive index, which is 1.5 divided by object distance. Object distance is r plus mu mr, r into 1 plus 3m by 2, writing mu as 3 by 2 equals difference in the two refractive indices. That means 1 minus 3 by 2. 1 minus 3 by 2, that is minus half divided by the radius of curvature. Radius of curvature of this. It's, see, the center of this lies somewhere here. So measured opposite to the direction of the incident ray. So plus r. Plus r. Got me? This becomes 0. This becomes 0. And from this equation, r will get cancelled and you can solve for n. You can solve for. Got me? Rajat. Simple. Read the next problem then, if you've understood this. If you solve for m, you should get 4 by 3. Read 21, please. Confusion है क्या कुछ? पक्का? अच्छा ठीक है. I derived the result real depth by apparent depth, right? O, refraction on a plane surface. I, this is the real depth. This is the apparent depth. Apparent depth, real depth. And I've said to you that real depth and apparent depth are separated by a factor mu. So you multiply by mu or divide by mu based on the ray diagram. Check which one is larger. So either way, either you're going to multiply by mu or you're going to divide by mu to get one from the other, right? See, in this case, I know the ray diagram suggests since it's bending towards a normal, I can see that this is larger than this, right? From air to glass, it's bending towards a normal. So this ray of light seems to be coming from I. So which is further away from this. So this is larger than this. So to get HA from HR, you multiply HR by a number greater than 1, which is mu. Right? I've done that in the class, right? Right. Read problem 21, please. A 3 times magnified image of an object is cast on a screen by a convex lens. And by the way, only a real image can be cast on a screen. Virtual images can't be cast on a screen, right? So the image must have been formed on this side of the lens. It's a real image formed by the lens. And since the magnification is 3, the image distance must be 3 times the object distance. The image distance must be 3 times the object distance. Now, if the object was placed here, somewhere like this, then the image is formed on the screen given that this is 64 centimeters. This is 64 centimeters. And this distance is 3 times this distance. That means this must be 3/4 of 64 centimeters. This must be 1/4 of 64 centimeters, right? So this must be 16 centimeters. This must be 48 centimeters. Yes or no? Right? So then, this is 16. This is 48. So when the object distance is 16, the image distance V is minus 48. So that gives us an opportunity to compute the focal length of the lens, right? So for the convex lens then, one by F is minus 1 by 48 minus 1 by U. U is plus 16. U is plus 16. So minus 3 minus 4, 12. So F is minus 12 centimeters. Yes or no? So the focal length of the lens is 12 centimeters in magnitude. So this is a 12 centimeter focal length converging lens. It's a converging lens because F turns out to be negative, right? Now the next part of the problem. The next part of the problem is a concave lens is then introduced between the convex lens and the screen. A concave lens is introduced between the convex lens and the screen at a distance 6 centimeters from the convex lens. Means right here, six centimeters from the convex lens, a concave lens is introduced. To focus the image again on the screen, the object has to be moved away from the convex lens through a distance of 15.2 centimeters. Obviously now, what transpires is, if you didn't do anything to the object, what's going to happen? This is the object, right? It would try and it would get refracted from this lens. It would have liked to converge to this point on the screen. But what happens is, it's intercepted by the concave lens. So the ray diverges and it's no longer going to. So this serves as a virtual object for refraction on this lens. And the image is no longer formed here, right? So it goes out of focus. In common parlance, we say that the image has gone out of focus. To get it back to this point, to get the image back to this point, what is done is that the object is moved away from the lens by an amount 15.2 centimeters. That means now the new position of the object is 31.2 centimeters from the convex lens, right? So now for the convex lens, the new object distance is 31.2 centimeters. If the concave lens was not there, let's see where the image of ON would have got formed. Suppose the concave lens was not there, let's see where the image of ON would have got formed. That would serve as a virtual object for image formation by the concave lens. How about that, right? So then for the concave lens, 1 by V minus 1 by plus 31.2, right? Plus 31.2 is minus 1 by 12 is minus 1 by 12, yes or no? Or we get like a 1 by V equal to 1 by 31.2 minus 1 by 12 minus 19.2 divided by 12 into 31.2. So V is minus 12 into 31.2 divided by 19.6, 7.8, 5.4, 19.5 centimeters, right? Minus 19.5 centimeters, that's where the image would have got formed. That's where the image would have got formed if this lens was not there. If this lens was not there, right? That means this is what would have happened. This. And if this lens was not there, the image of ON would get formed. The image of ON would get formed at O prime N. At O prime N, 19.5 centimeters from the convex lens. The image of ON would have got formed 19.5 centimeters from the convex lens. But this is 6 centimeters, so this must be 13.5 centimeters. This must be 13.5 centimeters. You might want to check my calculations. I may have made a mistake, but in any case, this would have got, if I have done that calculation right, it would have got formed 13.5 centimeters to the right of this lens, if this lens was not there, right? But this lens is there. This ray of light cannot mature into the lens along this path. What happens? It gets refracted from the lens. It gets refracted from the lens in a manner that instead of going like this, it goes like this and forms a final image here. See, it gets refracted from the lens to give the final image at I. To give the final image at I. Yes or no? So, for the concave lens, this ON serves as a virtual object. Virtual object. And what's the image of this ON? I. I is the image of ON formed by the concave lens. Yes or no? Yes. So, for the concave lens, now, this is the benchmark direction of the incident ray on the concave lens. What's U equal to? Minus 13.5 centimeters. Minus 13.5 centimeters is U for the concave lens. Yes? Right? U is minus 13.5 centimeters. What is V? V is, see, this is 6. So, V is minus 42 centimeters. This is 6 centimeters. This was 48 centimeters. So, V, the final image is formed at I. Right? So, V is minus 42 centimeters. So, V is minus 42 centimeters. You know V and U, you can compute F. From 1 by V minus 1 by U equal to 1 by F, you can compute the focal length of the concave lens, etc. Are you all there with me on this? Do you understand everything that I have said here? Yes. Yeah, why not? See, in this problem, you realize that when the object was O and it was just the convex lens present here, the image was formed at I. All right. Using that fact, we computed the focal length of the convex lens. All right. Now, a change was brought about. 6 centimeters to the right of the convex lens or concave lens was placed, and the image goes out of focus. Why? Because now the ray would have liked to converge at I, but it meets the lens here and it doesn't converge at I, it gets defocused therefore, right? Now to get the image back to I, the object is moved 15.2 centimeters backwards. So now for the convex lens, the new object distance is 31.2 centimeters. New object distance is 31.2 centimeters. 2 refractions occur, one here, one there, so that the image is finally formed at I, right? Now, for the first refraction, that is at the convex lens, taking u equal to 31.2 centimeters, we got v equal to minus 19.5 centimeters under the premise that the second refraction did not occur. That means this ray of light, after having got refracted from the convex lens, would have liked to converge 19.5 centimeters away from the lens. But that never happened. Why? Because this guy interfered. Now for this guy, for the concave lens, this serves as a virtual object. That means the object distance is minus 13.5 centimeters for refraction on the concave lens. Where is the image distance? The image distance, the problem itself says the final image after this change was brought about was again on the screen at I. That means for the concave lens, u equal to virtual object minus 13.5 centimeters, v formed at I, that means minus 42 centimeters. This is 6, that's 48, so this is 42 centimeters. So v is minus 42 centimeters. Using these numbers, we are all set to calculate the focal length of the concave lens. Pardon me? No confusion, right? Read problem 22, please. Sorry? Let me also read the problem. I would convex image coincides with the object. Yes, now tell me. No, point object. Point object. Shall I proceed then? So problem 22. Convex lens of focal length 15 centimeters is placed in front of a convex mirror. On the axis at a distance 20 centimeters from the lens. It is found that the image coincides with the object. Calculate the radius of curvature of the mirror, the separation between the lens. Oh, sorry. This is 5 centimeters. The object is placed 20 centimeters from the lens. This is 20 centimeters. Sorry, I stand corrected here. This is where the object is placed, 20 centimeters in front of the lens. The separation between the lens and the mirror is 5 centimeters. And it is found that the object coincides with the image. First of all, if this mirror was not there, let's find out where the image of O would have got formed, right? So, for the convex lens, if the mirror was not there, the image would get constituted at the image distance given by 1 by V minus U is plus 20 here, 1 by 20 equals focal length plus 15 or minus 15? Minus 15, because convex lens, it's a converging lens, its focus lies here, right? So, minus 1 by 15, right? So, 1 by V is like a 1 by 20 minus 1 by 15, 3 minus 4, so minus 1 by 60. It would have got formed 60 centimeters to the right of the lens. It would have got formed 60 centimeters to the right of the lens, right? This is what would have happened. That means if this mirror was not there, rays of light subsequent to having suffered refraction through the lens, they would have wanted to converge. They would have wanted to converge to some point O prime here. They would have liked to converge to some point O prime here, 60 centimeters from the lens. This is 5 centimeters, so this is 55 centimeters, right? Now the problem says that the final image is formed at O itself. That can happen if this ray of light retraces its path. If this ray of light subsequent to reflection from the mirror, retraces its path. Now, when can this retrace its path? When it's incident normally on the mirror? When would it be incident normally on the mirror? When this ray of light seems like passing through the center of curvature of the mirror, right? That means O prime must be the center of curvature of the mirror. That's when this ray would be incident normally on the mirror. So that means if this is the center of curvature of the mirror, the radius of curvature of the mirror is 55 centimeters. The ray of light, ray of light retraces its path and then settles back at O, and that's where the final image is formed. Got me? Right? Aritro? Got me? Yes, I will. I said, if this mirror was not there, this ray of light would have converged to O prime 60 centimeters to the right of the lens. Alright. But the mirror intervenes, this ray of light gets reflected and then gets refracted from the lens and a final image is formed. The problem says that the final image is formed at O prime. The image and the object will coincide provided this ray of light, which is incident on the mirror, if it's thrown back along the same line. See, if it's thrown back along the same line, then it will settle at O. That's reversibility of light. No? Now, when would it get thrown back along the same direction? When it's incident normally on the mirror? When it's incident normally on the mirror, angle of incidence will be equal to 0, angle of reflection will be 0. So, it will go back along the same direction, along the same line, but in the opposite direction, right? That means it must be incident normally. Now, what's a normal to the mirror? A normal to the mirror must pass through the center of curvature of the mirror. So, this is a normal to the mirror. When you produce it, it must pass through the center of curvature of the mirror. So, this, in the absence of the mirror, would have been O prime, the image, final image. But now, it's the center of curvature of the mirror as well. That's when it will be incident normally on the mirror. And when it's incident normally, that means this is the center of curvature. So, this must be the radius of curvature of the mirror, which is 55 cm. No, but then you don't want to use any more formulas here. I mean, now I know that this, of course, is a virtual object for the plane, for the convex mirror. But then, from considerations related to normal incidence, you can also conclude that this must also be the center of curvature of the mirror. And this would have been the image formed had the mirror not been there. So, we calculated this number based on that, 55. So, this is the center of curvature and therefore, this is the radius of curvature of the mirror. Right? Alright, 23. To stand by review. I have said so far. Huh? Alright. A concave mirror of focal length 20 centimeters is placed at a distance 25 centimeters from a concave lens. A pin placed 68.6 centimeters in front of the lens I mean, if this is behind, then I should regard this as in front, right? Forms an inverted image by the lens mirror combo coinciding with itself. Alright. Calculate the focal length of the lens. Okay. Again, the idea is simple. Rays of light that start from O rays of light that are starting from O get refracted from the lens to accommodate this ray. get refracted from the lens. It's a diverging lens, right? So they're coming like this and they're getting refracted like this, right? So as far as the mirror is concerned, they seem like coming from I. They seem like coming from I. Right? That means I is the image of O formed by the lens. I is the image of O formed by the lens, and that acts as a virtual object for the mirror. Right? That acts as a virtual object for the mirror. 20 centimeters is the focal length of this. The object is known to coincide with the image. That means this ray of light which emerges after refraction from the lens must be incident normally on the mirror, because you want this ray to retrace its path. A ray of light will retrace its path if it is incident normally on the mirror. That means this ray must be incident normally. When would it be incident normally? When would this be a normal to the mirror? When produced, I must be the center of curvature of the mirror. I must be the center of curvature of the mirror. The radius of curvature of the mirror is 40 centimeters. This is 25, so this must be 15 centimeters, yes or no? Right? This must be 15 centimeters. That means for the lens, I is the image of O. I is the image of O. That means when U is 68.6 centimeters, V is 15 centimeters. Yes or no? For the lens, O is the object, I is its virtual image. I is its virtual image. So, U is plus 68.6, V is plus 15. So, F, 1 by F would be 1 by V minus 1 by U. I don't mind repeating it if there are people who want me to do this. Yeah. Oh, okay. See, there is a ray of light that starts from here, gets refracted by the lens, and I is the image of O. I is the image of O. Alright. Now, the problem says that the image and the object coincide. When would the image and the object coincide? When this ray is incident normally on the mirror, then angle of incidence is 0, angle of reflection would be 0. So the ray of light, if incident normally, would retrace its path. It will go like this, and then from reversibility of light, it will settle at O. Then the image and the object would coincide with each other, right? And when would this be incident normally on the mirror? When this line passes through the center of curvature of the mirror. The radius of curvature is 40 centimeters. This is 25. So this must be 15 centimeters. This must be the center of curvature of the mirror. Right? So now, for the lens, for an object placed 68.6 centimeters, the image is formed at I, 15 centimeters. Right? So I know a U, I know a V, I can calculate F for the lens. So U is 15 centimeters, V is 68.6 centimeters, V is 15 centimeters. So I can calculate focal length from 1 by F is 1 by V minus 1 by U. I can calculate the focal length of the lens. Did you all get me right? See, these are really the ideas that you have to understand in geometrical optics. Time and again, we'll reuse this in various situations. So once you get a hang of it, geometrical optics is like peanuts. Very ordinary, very simple, and very scoring. Alright. So we've illustrated something across to you. I would now urge you to get started with the first problem of the sheet. And let's make some progress here. Get started with the first. I'm sure you've done some problems from the first page already. Yes. Sorry? Yeah, I'll solve everything. Just spend some more time on it, at least 15 more minutes. I'll solve, at least attempt the first page. I'll solve everything in the first page in 10 minutes for you. Huh? Sorry? Draw the ray diagram and see what happens when it gets reflected. See, inverted तभी देख सकोगे जब एक extended object लोगे. Principal axis पे ना एक point object के लिए inverted और erect का कोई मतलब. So just draw a ray diagram for an extended object. So what does the problem say? Draw एक extended object लेके ray diagram बनाओ, तब समझोगे. Just draw a ray diagram. Problem 1. Two plane mirrors are inclined to each other at an angle of 60 degrees. If a ray of light is incident on the first mirror, parallel to the second mirror, parallel to this mirror, 60 degrees, gets reflected like this. This is 60 degrees. And then like this. So this is also 60 degrees. And it runs parallel to the first mirror. Runs parallel to the first mirror. That's what happens, right? So option B. Option B. Clear? So problem 2. Two mirrors are inclined at an angle theta. The ray will start retracing its path after the third reflection. The ray starts retracing its path after the third reflection. Okay. See the grazing angle after the third, if this angle is theta, right? Then after reflection, this will be theta. And these are grazing angles, right? So the grazing angle after the third reflection, would be I1 plus 3 minus 1 into theta. Remember this result, right? That is 3 theta. And since it starts retracing its path, that means this grazing angle must be 90 degrees. See, this is the first reflection, second reflection, and this is the third reflection. Right? This must be the first, second, and this must be third. So in this case, for it to retrace its path, this must be 90 degrees. So grazing angle must be 90 degrees. Angle of incidence is 0, but grazing angle must be 90 degrees. So this is I3. That's 3 theta, right? And this must be 90 degrees. So theta must be 30 degrees. In is I1 plus n minus 1 into theta. The grazing angle becomes 90 degrees so that it could retrace its path. The grazing angle, this angle must be 90 degrees, I3. Theta must therefore be 30 degrees. Got me? So, option B, option Bombay for this, right? I hope I discuss inclined mirrors. Huh? Two plane mirrors are parallel to each other and spaced 20 centimeters apart. An object is kept in between them at 15 centimeters from A. So this is A, let's say this is B. This is the object O, kept 15 centimeters from A, 5 centimeters, right? Out of the following, at which points the images are not formed in mirror A, distances measured from mirror A, right? Again, two series of images. Why two series of images? The first series, where first reflection occurs here, the image of this serves as the object for this, the image of this serves as the object for this, and so on and so forth. That's the first series of images. The second series of images would be first reflection here, the image formed by this serves as the object for this, the image formed by this serves as the object for that, and so on and so forth, right? So let's say the first series of images. Let me look at the first series first. First series, let's say first reflection here, and then second reflection, and then third reflection. Okay. Now, in the first series, the first reflection here, so for O, the object distance is 15 centimeters. Let's say the O1, the first image is 15 centimeters behind it, right? And this O1 serves as the object for this. Now, object distance is 20 plus 15, 35 centimeters. So the image distance O2 from B, the object distance is like 20 plus 15, 35. So this would be 35 centimeters, right? Now O2 serves as the object for this. So now object distance is like 35 plus 20, which is 55 centimeters. So image distance O3 then would be 55 centimeters. And then 55 for this serves as an object. So 55 plus 20, 75. And then O4 is like 75 centimeters, and so on and so forth. This is the first series of images, and so on and so forth, right? So this becomes 95 and then 95 below this. Then 95 plus 20, 115, 115 above this, and so on and so forth, right? Do you understand how these images are formed? Right? Now the second series of images. In the second series, first reflection here, right? So image of O first formed by this at O1, 5 centimeters. This serves as a virtual object for this. So 5 plus 20, 25 centimeters. So O2, 25 centimeters, right? This O2 serves as an object for this. So 20 plus 25, 45, 45 here. O3, 45, and then 45 plus 20, 65 for this, and 65 below this, O4, 65, and so on and so forth, right? You know what I'm doing here? So now let's just check out the options. You can keep constituting images this way, the first series and the second series. The problem says, out of the following, at which point the images are not formed in mirror A, distances measured from A. 15 centimeters? No, it's formed 15 centimeters. 25 centimeters from A? Look at this. Yes, it's formed 25 centimeters. 45 centimeters from A? No, it's not formed. See? 45 centimeters from A, no image is formed. So this option is right. C is right. 55 centimeters from A, is there an image formed? Yes, there is an image formed. So option C. Option C. Bolo, bolo, bolo. No confusion, right? So option C. You don't see an image formed by A 45 centimeters from A in any of the two series. In any of the two series. That image is not available, right? From A formed by A. Clear? Let me look at problem 4. So how many of you got this right? A point object is kept in front of a plane mirror. Is kept in front of a plane mirror. The mirror is doing SHM of amplitude 2 centimeters. The plane mirror moves along the x-axis, and the x-axis is a normal to the mirror. Along this x-axis, the plane mirror executes simple harmonic motion of amplitude 2 centimeters. The amplitude of the mirror is such that the object is always in front of the mirror, right? That means, the mirror doesn't go past the object. The mirror doesn't go past the object. The amplitude of SHM of the image. Okay. Let's say this is the mean position of the mirror. This is the mean position of the mirror. Alright. And in the mean position, the object is at a distance x from the mirror. The object is at a distance x from the mirror, and the image would also be at a distance x from the mirror, right? For the mean position. X obviously would have to be greater than 2 centimeters. X would, otherwise if it's less than 2 centimeters, the mirror would have gone past this in its amplitude, alright? So X obviously would have to be greater than 2 centimeters. Now, when the mirror reaches its extreme position, this is the extreme position, rightward extreme. This is the rightmost extreme. Rightmost extreme. This is the rightmost extreme. Then it would have shifted by how many centimeters? 2 centimeters. That is the amplitude of motion. Right? Now, the new object distance then becomes x plus 2. The new object distance in this position is like a x plus 2. So the new image distance would also be x plus 2. So the new image, I at the amplitude position, measured with respect to this position of the mirror, is going to be x plus 2. X plus 2. Right? Object distance is x plus 2. So image distance would also be x plus 2. Now, this distance therefore is x plus 4. Right? Another 2 centimeters. So distance from the original position of the mirror of the final image would be x plus 4. Right? And therefore, this would be 4 centimeters. This would be 4 centimeters. Right? That means when the mirror has moved by its amplitude 2 centimeters, the image has moved by 4 centimeters. That means the amplitude of the image must be 4 centimeters. Amplitude of the image must be 4 centimeters. Got me? Huh? How many of you got this right? Oh, good. A person's eye level is 1.5 meters. He stands in front of a 0.3 meter long plane mirror, which is 0.8 meters above the ground. The length of the image that he sees of himself. Right? This is the mirror. It's given to be 0.3 meters and is placed 0.8 meters above the ground. This is the ground. The person's eye level is 1.5 meters above the ground, right? So this is 1.1, so higher than this is 1.5. So the eye level of the person is somewhere here, which is like 1.5 meters, which is like 1.5 meters. The length of the image that he sees of himself. What you would have to do is, you'll have to identify the extremes of his own self that he can witness through the mirror in his eye, right? That means the extreme rays would be the rays reflected from the edges. The extreme rays would be the rays that are reflected from the edges and enter the eye, right? So let's say from the upper edge, what's the extreme that he sees? This is the extreme ray from the upper edge. And this realize is 0.4 meters. That means one extreme that he sees is point A of his own self, right? It hits this edge and reaches the eye, and realize that this is 0.4. This is 0.4. So these two triangles are congruent. So this must also be 0.4. This must also be 0.4. Right? So, and this is 1.1. This is 1.1. See? 0.8 plus 0.3. This is 1.1. This is 0.4. So one point that he sees of himself is like 0.7 meters above the ground. One point that he sees of himself is 0.7 meters above the ground. Right? Let's identify the other extreme that he sees of his own self, right? One point is A, 0.7 meters above the ground. Let's find out the other extremity, that means the ray that comes from this edge. Now I'll just wipe this off. Just remember, it's 0.7 meters, one point that he sees. The other extreme that he sees of himself through the other edge the ray of light coming from the lower extreme of the mirror. The ray of light coming from the lower extreme of the mirror. This is 0.8, so this is 0.7. So this is 0.7. So he sees the other extreme B, which is like 0.1 meters, right? So one point that he sees of his own self is A, which is 0.7 meters above the ground. The other point that he sees of himself is B, which is 0.1 meters above the ground. That means he sees everything between A and B, which is 0.6 meters, 0.6 meters. So he sees 0.6 meters of his own self. He sees everything between A and B, which is 0.6 meters. So his own length, he can see only 0.6 meters. AB. A and B are the extreme rays that enter his eye. And everything between A and B is visible to his eye. And that's like 0.6 meters from ordinary geometry. Fair enough? How many of you got this right? Six. Can I write this off? A person is standing in a room of width, that means length or whatever, 200 centimeters. A vertical plane, a plane mirror of vertical length 10 centimeters. Is fixed on a wall in front of the person. This is the wall. The person's eye is here. And the person is 50 centimeters in front of the mirror. We do not know where the eye is exactly located. So let's say this is X and this is 10 minus X. 10 minus X. Right? And this distance is given to be 200 centimeters. This is 200 centimeters, right? The person looks into the mirror from 50 centimeters. How much width of the wall or the height of the wall behind him will he be able to see? Obviously, rays from the extreme edges. So he is able to see point A of the wall. Because of this reflection, right? Okay. Now this is X, and realize that these two triangles, this triangle and this triangle, they are similar because this angle equals this angle and 90 degrees, right? And the ratio of their sides is like 50 is to 200. 1:4. Ratio of their sides is 1:4, right? These two triangles are similar. This is 50, this is 200. So ratio of their sides is 4. So if this is X, what would this be? 4X, absolutely. This would be 4X. Right? This is 10 centimeters. Now, from similar considerations, he is able to see the other extreme that he sees is the point B. Now, like before, this is 10 minus X. The only difference between this situation and this situation is, instead of X, you have 10 minus X. So now, this length is going to be 4 into 10 minus X. So he is able to see everything between A and B, right? So we have 4x plus 10 plus 4 into 10 minus x. That makes it 50 centimeters. That makes it 50 centimeters. He sees 4x will get cancelled, 40 plus 10. 50 centimeters of the wall is what he is able to see. Everything between A and B. Rays appearing from the extreme edges into his eye. Got me? 50 centimeters between A and B. Okay, at least I know you're silent today for several reasons, but let's at least solve one more problem, one more conceptual problem, and then I'll let you go. Okay. See, one important thing is, can I wipe this off? Very simple little thing though. Can I wipe this off? Huh? We could have a situation where the object is in motion, the image is in, the mirror is in motion, and therefore the motion of the object and the mirror would connive to dictate the motion of the image, right? Let's identify simple kinematic principles that will tell you the motion of the image given the motion of the object and the motion of the mirror, no matter how complex it is. Okay. Say this is a plane mirror. This is an object and line perpendicular to the plane mirror, passing through the position of the object. Let's say the mirror has a velocity Vm. The mirror has a velocity Vm. The object has a velocity V0. The object in general has a velocity V0. Now we have to deal with the velocity of the image. Velocity of the image. The image, let's say, has a velocity some Vi. The image has a vector velocity Vi. Now, the important consideration here is that if you are sitting on the mirror, if you are sitting on the mirror, if you are an observer on the mirror, then in a certain time, if you find that the object has advanced towards the mirror along the normal, if you find that the object has advanced towards the mirror in this direction, then the image would have advanced towards the mirror in the opposite direction along this line. That would have certainly happened. As far as this direction is concerned, this observer would tell you that the component of the velocity of the object, or rather the velocity of the object in this direction must be negative of the velocity of the image along this line. You know what I'm saying? Suppose along this direction there is a unit vector n cap. Suppose there is a unit vector n cap in this direction, right? Now, this, when there is an observer on the mirror, then it's like you are reducing the mirror to rest. If you reduce the mirror to rest, you would have to adjust the velocity of the object and the image. The velocity of the object must then be v naught minus vn, must be v naught minus vn. The velocity of the image must be vi minus vn, must be vi minus vn, right? What does the mirror see of the object and the image? The relative velocity of the object and the relative velocity of the image, right? What would the mirror perceive? And when I'm pinning the mirror and I'm making an observer observe things about the object and the image, it's as if I'm trying to have a reporting on the relative velocity of the object and the relative velocity of the image as perceived by the mirror observer, as perceived by the mirror observer, right? That's what it means, right? So, if I choose to create an equivalent situation where I hold the mirror to rest, then it's important that I make amends to the velocity of the object and the image, right? Which means, now this becomes, what would the mirror see? The mirror would see the velocity of the object with respect to the mirror, right? It would see velocity of the object with respect to the mirror. The mirror would see, not v naught, the mirror would see velocity of the object with respect to the mirror. The mirror would see for the image, not vi. This is the absolute velocity of the image. But what would the mirror see? The mirror would see velocity of the image with respect to the mirror. This is what the mirror would see of the object and the image. But what's velocity of the object with respect to the mirror? v naught minus vn. Velocity of the object with respect to the mirror would be velocity of the object minus velocity of the mirror, right? Velocity of the object minus velocity of the mirror. That's the relative velocity of the object with respect to the mirror, right? Velocity of the image with respect to the mirror. Vi minus vector difference between this and this, right? Now, so this is the perception of the mirror about the object and the image. The kinematic status of the object and the image is this as perceived by the mirror. As perceived by the mirror. Alright. Now, this velocity has a component in this direction. This velocity has a component in this direction. Right? Suppose this direction is referred to as n cap. Is referred to as n cap. What's the velocity of the relative velocity of the object in the direction n cap? What's the relative velocity of the object in the direction n cap? Dot n cap. Dot n cap, right? Velocity of the object with respect to the mirror along the direction n cap would be this dot n cap. That's the component of this velocity in the n cap direction. No? Right? What's the velocity of the image with respect to the mirror in the n cap direction? This. Right? Do you realize they should be negative of each other? They should be negative of each other, because while the object goes like this, the image goes like this. The component of this is in the positive n cap direction, whereas the component of this is in the negative n cap direction. So these must be negative of each other. Right? These must be negative of each other. No? That means velocity of the object with respect to the mirror dot n cap must be negative of the velocity of the image with respect to the mirror in the n cap direction. Why must they be equal in magnitude? Yes, they have to be equal in magnitude, because if in a given time the object comes closer by 2 centimeters, the image would also have to come closer by 2 centimeters. So their velocity components are directed oppositely, but would have to be equal in magnitude along the n cap direction, Are you there with me on this? Do you all understand this? This then would be the underlying principle for the next problem. This then would be the underlying principle for the next problem. Alright. I will leave this discussion here so that you can go back home and attempt the next problem in line with this discussion. Yes. No, they're not moving in the same. They are moving along this in opposite directions. Because see, if the object distance decreases, the image distance also decreases. So it's opposite directions that they are moving. Okay. I'll quickly tell you what they are doing. Now, the reason I gave you this vector stuff is so that you don't have to apply your heads. It's a ready reckoner that I offered to you. But in principle, think of it like this. Suppose the mirror is fixed. Alright. This is an object, this is an image. Right? If the velocity of the object is simply let's say along this direction, velocity of the image is along this direction, just this direction, and let's say the mirror is fixed. And when I say the mirror is fixed, then these velocities are like relative velocities. Then V0 and Vi would be like relative velocities, alright. So then, one thing, if they are moving along, if the object is only moving along the normal direction, then can I not say that V0 must be Vi? Can this be said? V0 must be minus Vi. It can't be equal to Vi because if the object is coming closer, the image will not move further. So V0 can't be equal to Vi. V0 and Vi are equal in magnitude but oppositely directed vectorially. Is this alright? The next thing is, suppose, so this is situation 1. Situation 2, suppose the object is moving like this. Suppose the object is moving like this, has no velocity here. Then, and the image would also have a velocity. Do you realize that the velocity of the image would be like this, and V0 must be equal to Vi, and V0 must be equal to Vi? Yes or no? In this case, V0 must, if the object moves up, the image will not go down. If the object is moved up by 2 centimeters, the image would also go up by 2 centimeters. It's not going to go down by 2 centimeters. So V0 and Vi in this case must be equal. Right? Now a combination of the two, right? Which means this has a velocity like this, this has a velocity like this, this has a velocity in this direction, has a velocity in this direction, the image, right? Then this you can equate to this, and this must be negative of this vectorially. That can be said, right? Where, what is this component? This component is in a plane which is perpendicular to the perpendicular. This velocity is in a plane, this plane, which is perpendicular to the normal direction. Yes or no? Right? So if the normal direction is the z direction, then this velocity must be in the xy direction. This velocity must be in the xy direction. See, if this is regarded as the z direction, then this velocity must be in the xy plane. This velocity must be in the xy plane, right? That means the velocity of the image in the xy plane and the velocity of the object in the xy plane, that must be the same. That means their ij components must be the same. Where will they be different? They would be different in their k components. They would be different in their k components. You know what I'm saying? where what are these velocities? These velocities are on the premise that the mirror is pinned. When the mirror is pinned, then these velocities are actually the relative velocities of the object and the image in the shown direction. You would want to make headway in the problem after this, right? So think about this problem. Once you go back, I have given you enough juice to be able to solve this problem independently. The vector stuff that I gave and the qualitative stuff that I offered here, you just paste them together and you'll be able to solve the next problem. Alright?